All right, in this video, I really just wanted to reiterate and do some practice on solving equations in general. We took some big jumps last week in our connection between solving equations, particularly solving linear equations in two variables. We did a jump between connecting solving equations and graphing. But right now, let's take a step back. Let's take a step back and let's just look at some quick examples and work through some quick examples for solving equations. I'm literally just going to make up some equations on the fly here. Actually, let's make this a little bit less complicated, 5. All right, I haven't thought deeply about these numbers at all. I just wrote some numbers down with some variable term here. So this is a linear equation in one variable. To solve this, we would want to isolate x. Isolate is a fancy word for make it alone on one side. So isolate it. So what we're going to have to do is we're going to have to get rid of the constant that's on the same side as the x term. Now, I will say here that order technically doesn't really matter. If you wanted, you could get rid of this 2 first. You could get rid of this 2 that's being multiplied against the x variable. You could do that, and I'll show you what that would look like. So if you want to get rid of the 2 that's being multiplied by that is multiplying against the x, what you would do is you would just divide by 2. But you can't just divide, you can't do this. You can't just divide this by 2 like that. You can't just divide a single term on one side of an equation by anything you want. What you have to do when you're making these choices of adding on both sides or subtracting on both sides or multiplying or dividing on both sides, what you have to do is you have to do that to the whole side. So if you're dividing by 2, make sure you do it to both of those numbers. So I'm actually going to do this the hard way first and then the easy way second, just showing you that order doesn't matter. You could get rid of this 2 first. So if we do that, then we have to somehow start to play around with this big fraction on the left here. And one thing that we can do is we can rewrite it. We can rewrite this big fraction as simply 2 fractions with the same denominators. So I'm just going to write 2x minus 3. So 2x is this term. It has a denominator of 2. I'll write that down. And negative 3, that also has a denominator of 2. I'll write that down. So I've simply just separated these 2 fractions. I could recollect them together again, right? Because these 2 fractions have the same bottom number. They have the same denominator. I could recollect them, but honestly, there would be no point in doing that because then I would just have the same number that I started with. And so separating them like this will be useful because we can see here that these factors of 2 on the top and on the bottom will cancel or divide out to 1. So I just have x left over. And then I just have plus negative 3 over 2. And then on my right-hand side, I still just have 5 over 2. I'm going to make some room here. I'm going to rewrite my left-hand side, but I am going to clean it up a bit. So I just have x left here with this particular term. And then I have minus or plus negative, doesn't really matter how you write it. You can say minus or plus negative. They're really saying the same thing. They are equivalent. Minus 3 over 2 equals 5 over 2. Now I can add 3 over 2 to both sides because, again, I want to isolate this x term here. So add 3 over 2 to both sides. Let's simplify this now. So I've added 3 over 2 to the whole left-hand side. Now I just have x left. Then I have 5 over 2. Now plus 3 over 2. And I can collect both of those numerators under the same denominator because it's the same bottom number. And here it's clear that 5 plus 3 is 8. And I can simplify again. 8 over 2 is 4. And that would be my final answer. Now that is a heck of a lot of steps. It's the true solution. You could try plugging 4 back into this x term. 2 times 4 is 8. Minus 3 is 5. This would give us a true equation, so it's a good solution. I'm going to show you why, although order doesn't matter, order can make things easier on you. So if you don't want to get rid of the constant first, here, if you don't want to get rid of the constant first, and you instead want to get rid of the coefficient in front of the x term, you can totally do that just like we did, but here's an easier way to do it. Just get rid of the constant first. That's why we tell you in the previous lessons, get rid of the constant that's on the same side as the variable term. Because, well, we see that these 3's will cancel on the left-hand side. What's left on the left-hand side? 2x. What's left on the right-hand side? Well, 5 plus 3 is 8. And now we can get rid of this coefficient of 2 by dividing it out. 2 divided by 2 is 1. X equals 4. Hey, that's a lot easier. So that's just showing you that although order doesn't really matter in terms of what operations you're choosing to apply on both sides to eventually isolate your variable term, although order technically doesn't matter, it can help, right? Order doesn't matter in terms of whether or not you're going to find a true or false answer. It can just make life easier on you. I'm going to quickly try another question. So I'm going to quickly try another question. Let's just do 3x minus 9 equals 2x plus 5. Now here you might be tempted to call this, a two-variable linear equation, but it isn't. There is really only one variable here. It's just in two places. The variable is x, so this is really a one variable. This is a one-variable equation still. And what we're going to need to do is we're going to need to isolate. We're still going to need to isolate the x variable. And to do that, we're going to need to collect these two x variable terms into one term. So let's collect these like terms together first. How do we collect these like terms? Well, let's make sure that they're both on the same side first. So let's bring this variable term to the left-hand side. It doesn't really matter if you bring the 2x to the left-hand side or if you bring the 3x to the right-hand side. You'll get the same answer either way. It's just this way will be easier. All right, so now I have, oh, I don't want the keyboard there. Now I have 3x minus 2x minus 9 equals what's on my right-hand side, 5. And now I can collect these two like terms. If I have 3 x's and then I take away 2 x's, how many x's do I have left over? I just have 1 x left over. Minus 9 equals 5. So here I just collected these two like terms. Right? And you collect like terms by adding or subtracting their coefficients. So 3 minus 2 is really 1. So I have 1x left over, but we don't need to write a coefficient of 1. It's implied. All right, so let's now work on this. We have x minus 9 equals 5. Our goal is still to isolate this x term, so we have to get rid of this 9. So we add it to both sides. And when we simplify the left-hand side, we can see that it's just x left over. And when we simplify the right-hand side by collecting these two constants together, we can see that x equals 14. And that's our right answer. So hopefully it's helpful to have these two other examples. One example where hopefully I showed you that while order doesn't technically matter for finding the correct answer, order can help to make the process simpler, getting rid of the constant first and then getting rid of the coefficient in front of your variable term. And hopefully in this particular example, hopefully I demonstrated how if the same variable pops up in two different terms on two different sides, you can just collect the variable, all of the variable terms on one side. Here we collected all the variable terms on the left-hand side. And then after doing a little bit of algebra, we simplified by collecting those like terms and then got rid of the constant on the same side as a variable term, and we found our solution. So hopefully those were instructive examples. We're going to push this even further in the next video.